Because it's next to a lone pair. We can do resonance, yeah? I'm not going to draw a resonance structure to actually be major. That's why we put cations there. This is 15, so this is M minus 15. All of these are 88 if you add them up. So 88 minus 15 is what, 73? So we expect to peak at 73. Now if you cleave here, it's the same thing, and here it's the same thing. Can you cleave, do you cleave here on the other side? No, that would not give a cation next to a lone pair. You would have cleaved all that. But if you make this a CH2H, that's what a methyl is, you could cleave here. CH2 cation plus H radical. And guess what? That's a cation next to a lone pair. And this is M minus 1. This should be what, 87? You can cleave an H radical. That would be just, okay.
Could you also cleave an ethyl here, or that?
And ethyl? There's really no ethyl in the compound. I mean, cleave where, you talking?
Just, oh, I guess you can't because they're all joined at the alpha carbon. So you can only cleave one methyl at a time. Rather than two.
Now, that was alpha cleavage. Okay? Cleaving between an alpha and beta. Okay? The first carbon from your functional group is alpha, and the next would be beta, but that's kind of like a beta. We cleave between the alpha and the beta. We cleave between the alpha and the beta. All this is putting cation next to a lone pair. We could also envision just making cleaving here. This is not really alpha cleavage, but if we cleave there, we would get what? We can envision making this nice cation plus the O-methyl, and the O-methyl would have to be a what? Radical. But that's a nice tertiary. It's not alpha cleavage, but it's still a good cation, and this is what going to be, 45? Pretty sure that's 45. See, 4 carbons is, no, that's 48 right there. 48 and 9, that's 57. 57? 4 carbons, 48, 9 H's. I think that's 57. Okay. So that molecule we expect 87, 73, and 57. What do we expect for the second one? Let's do it over here. Hopefully you've got this. I can cleave here. I'm going to call that A. If I cleave there, we get boom, boom, O-methyl, cation there, plus we cleaved off the methyl radical. Why is that a good cation? Because it's next to a lone pair. This is M minus 15. Well, that's also M minus 15. 73? Okay. Where else could you cleave?
On the other side.
Other side. Call that B. And we would get O-methyl cation here. We cleave the other, which is going to be ethyl radical. This would be M minus 29 ethyl radical. 88 minus 29 is 59. Cation next to a lone pair, cation next to a lone pair, but it's 2 different cations. I can envision losing the H if I cleave between the CH2 and the H. I'm not going to do that one. Let's see if we need to later on. I got something different here. Over here I had a 73, but I didn't have a 59. That one I expect a 59. How about the top one? Where do we expect to cleave? Same thing. We can cleave an H and make a CH2 cation. Over here we would cleave where? Here. I'll try to draw it up top here. Boom, boom, plus boom, boom. Cation would be there next to lone pair. This would be radical. We lose the propyl radical, we make this. This is M minus propyl's got to be 43, and it's 3 times 12 is 36. 2, 4, and 7, 43. No, that's M minus 43. M minus 43 equals 45. these could lose an H like we did there. All these we get 87, 'cause, okay? It's really not going to help you, because they all get 87. Did we have a 45 down here? No. Over there? No. So that one we expect 45. Now let's look at the mass spec. Well, do you see one that has a 45? The last one does. And we don't expect that for any of the others. So if you number these as 1, 2, and 3, the last one I'm thinking is 1. It has a 45. What is 56?
That's the 32, would that be the property?
What?
And to get 56, you have to lose 32. So
We have to lose 32.
That's the
Molecular weight's 88. 56 is not going to be a cation, because the cations would be odd.
So is it the new property?
Factory is only for carbonyl compounds.
Okay.
These are alcohols. These are ethers. Now, you can do something analogous to mercaptane, but it's not called mercaptane. Mercaptane is carbonyl compounds. 56 is not going to be a standard cation. All cations would be odd. Even molecular weight, okay, that's sort of like the nitrogen rule. Not quite sure 56 is. We don't expect 56 for any of the others. But we expect 45 only for that one. Let's tentatively say that's 1. We're done. That's compound 1. Okay, compound 2, we expect, that was over here. We expected alpha cleavage, we expected 73. That's the loss of the H. 73 should be like the main alpha cleavage. Does one of them have 73 as the main?
Yeah.
Both have 73. By the way, this happened to be labeled for you, because these came from a textbook. They're not going to be labeled for you on like quizzes, tests, and everything. You don't have to see what that is. Both of them 73, but we also, difference is, this one is 7359, that's 73 and something else. Uh-oh. 7359. 7359. Which one is this? Compound 2, this is compound 2. With 59 being a expected alpha cleavage, 73 also there. Why is 59 better cleavage than 73? They're both resonance stabilized cations. Has to do with the radical. This radical is more stable than that one because this radical has a donating group. Remember, radicals are like cations. Donation stabilizes them. Even though that doesn't show up in the mass spectrum, it still shows up in terms of its energetics and how it drives the reaction. Now hopefully the top spectrum has some of these numbers for number 3. Does it? Has 73. It has 57, which is that T. Okay. I initially got it wrong. It's 57. The other one was lost at H, 87. Does it have 87? I mean, there's a little bit. You could maybe say that's lost to the H. Well, that one really didn't have it. I don't know why. They all should potentially lose an H from that methyl. I mean, that's it. Do we have to interpret the rest of the peaks to do what we were asked to do, to assign each compound to a spectrum? No. Why didn't we look at the 88? Because they're all 88 if you look at them. They're isomers. That's not going to help you distinguish which is which. Now, if that was 88 and this was 102, well, that's all you'd have to look at. Right? Questions about that page?
Why for some of the mass spectrums, the molecular ion peak doesn't show up?
Because the molecular ion is not that stable. It will cleave before it hits the detector. When would it not be that stable? Whenever cleavage is very easy to do. It wants to cleave real quick. When does it want to cleave real quick? If the resulting cation that can be formed is very stable, it's going to want to break apart to that cation. The only reason it won't cleave quick is if where it's going is not that good. It just wants to stay together. All those we saw at 88. It's real small. Sometimes you may not. If you don't see it, then it becomes a little bit more difficult. What is your mass? But you can still use cleavage peaks. Okay, there's others to work in the workbook. Please note in the workbook there's also some combination problems where you get both an IR and a mass spec to determine what compound we're talking about. Let's look at one of those real quick. Actually, let's look at one of those tomorrow. I'll tell you, basically, look at those, okay? Where an IR is given as well. And I think in one of those, there's no formula given. All you're given is just the mass and the IR is just asked you what the structure is. Okay. Let's start elimination. Maybe after a short break today, we'll go back and see if we can look at Diels-Alder or anything. Okay, elimination. You had down here. Here's an example of elimination in the synthesis. What do we synthesize? Tamiflu. Tamiflu. Right here is a E2 elimination. Got this compound with an iodine. They're treating it with DBU, which is a nitrogen base, a neutral nitrogen base. THF is a solvent. Reflux for 12 hours. What are they doing? Well, there's two H's here. There's only one there now. And the iodine's gone. If you just do formula, we have lost an H and an I. What type of reaction is this? Elimination. We're eliminating HI. We're not adding anything, we're eliminating. Are we doing a substitution? Are we replacing one of the atoms with something? No, we're not replacing the atoms with anything. We're just removing atoms. We're eliminating. And when we get to elimination, it's the opposite of what? It's not the opposite of substitution. The opposite of elimination is actually addition. So the elimination reactions are going to be the reverse of our alkene addition reactions for test 2. And in test 2, all those were, you started with an alkene and you added something. For example, maybe you start with an alkene. If you start with an alkene and you want to get this, what do you have to add to it? HI. And we know how to do a mechanism for adding HI. Okay? That would be addition. We're doing the opposite. We're going back to an alkene. So elimination reactions typically give alkenes. I only say typically. It always gives a pi bond. For us, it's mainly going to be carbon-carbon pi bond alkene. You could theoretically eliminate and make a carbon-nitrogen pi bond, but that would not be an alkene. But it's still the same idea. We're going to call this E2 because we're going to have both E1 and E2. We already know the difference between the 1 and the 2. 1 is unimolecular, 2 is bimolecular. Down below there's an E1 mechanism. It's a little bit more complex in going from, well, they're doing multiple things here. This is an E1 where they're eliminating this Bach group. Bach is defined over there. They're eliminated. Then they also make the salt, the phosphoric acid salt of the basic nitrogen. So it's a little bit complex. You can look back at this. This is the N-Bach. Bach stands for butyl oxycarbonyl. And the acid, this is all the way. We actually eliminate this group It's eliminated off, and the O just becomes an H. You can look back at that. This group ends up being alkene. Except that's actually the minor component. The major component is your other portion. So it's a little bit convoluted, but once we see what E1 is, maybe you can look back at that. Before we move on, general statement over here. This oxygen needs to leave that carbon. There's that carbon. The oxygen is now gone. The oxygen was a leaving group. How do you make oxygen a better leaving group? Protonate it with what? Acid? Well, that's why it says H+. And what acid did they use in the reaction? Phosphoric acid, right? Okay, let's look at this. Beta elimination. It's called beta elimination. We'll define why. Just like our substitution reactions, you only do this at tetraneutral carbon. That is, the leaving group, these reactions will also have leaving groups. The leaving group must be on a tetraneutral carbon. Here's a general line reaction. You've got a carbon with a leaving group. You treat it with a base. The base is going to have a lone pair. You eliminate the leaving group, but also one of the hydrogens. Because there's one remaining hydrogen. We just removed one. We also removed the leaving group. And when you remove those two, you end up with a pi bond between the two carbons. Why is it called beta elimination? Because the H that's eliminated is on the beta carbon. If that's the functional group, the first carbon's alpha, the second one is beta, you're eliminating an H that's on the beta carbon. So it refers to the H position that's being eliminated. It's called beta elimination. Ultimately, in this scenario, the base is going to end up with the H, and the leaving group is just going to leave. Now, how does this all happen? We'll show two different mechanisms. Here's a precise example. Here, X could be bromine. It could also be iodine, chlorine. Not fluorine. Fluorine's a bad leaving group, right? This would be a good base. Oxygen anion. And so we can beta eliminate, make the alkene. The base gets the H. And so when it gets an H, it's actually now neutral. And the leaving group just kind of left as a Br minus. So that's a precise example. Some terminology. Whenever the leaving group is a halogen, it's called a dehydrohalogenation. D means you're removing something. What are we removing? We're removing the hydrogen and a what? A dehydrohalogenation. Makes sense, right? But it's terminology that if you don't just see and recognize, whenever you hear it, you won't. Okay? All right, so let's look at two possible mechanisms for this dehydrohalogenation reaction. Let's do what's going to be called E1. E1, the first step is just like SN1. What's the first step of SN1? Leaving group leaves. That is, this just leaves. If it just leaves, what do we get? We get that plus Br minus. What do you think of this mechanism so far? Well, Cosine, what do you think of this mechanism? You liking it so far, or all of a sudden you don't like it? Why don't you like it?
No, it's fine. Similar to this.
Anybody not like this? Why don't you like it, Zach?
I don't like that leaving group just leaves.
You've never seen a leaving group just
I
leave?
mean, I have, but I don't like it.
Why don't you like it?
What prompted it to do that?
When you put HBr in water, what happens?
Yeah,
It leaves?
yeah.
Okay. Well, what prompts this to happen?
I would think
that.
that the oxygen lone pair, like I always thought the oxygen lone pair would break apart the H, making it BRE.
Bonds to the H? Yeah. So it's really been more than just misleading?
Yeah.
You're right, but a lot of times you just see things ionized. Okay, if you put HBr in water, it does it, it ionizes. If you put HBr in hexane, will it ionize?
I don't see why I wouldn't.
Why does it ionize in water?
Because it's polar.
Because water's polar, and ions are supported in a polar solid. But you get all this hydrogen bonding and dipole-dipole interaction. Okay? Leaving groups will just leave. One thing we can say, though, is the more polar the solvent, the more prone they're going to leave. But guess what? That's not what that picture is for. Okay? Things can just ionize and leave. I thought you were going to say you didn't like this particular ionization. Why don't you like this one here?
Primary.
Primary cation, bad, right? I thought you were going to say you don't like it because it's bad cation. Well, let's first do this and then step back. Because if we're going to do this mechanism, we've got to form Br minus. And there we go. I just showed you a possible way to form it. But what else do we also need to form? Or do? We also need to remove an H and put in a pi bond. Well, at this point, the base could bond to the H, and I could show these electrons just moving in. And what does that arrow movement do? What does this mean? Electrons are moving in to make pi bond. And what does that mean? Yeah. See, all that, you're home. All that gives you your other two products. Okay, define the two steps. The first step is what? Ionization. What do you want to call the last step? Base takes the H in your home? Yeah. The last step is actually called beta elimination. Now, you may say, I thought the whole thing was called beta elimination. It's sort of, that's the beta elimination step. That's where you eliminate the beta hydrogen. Yes, the whole thing is called beta elimination, but see, that's the step where you eliminate the H. And when you eliminate it, the two electrons, see, that just bonds to the H. Where do the two electrons go?
Swung down.
They sort of fall in and make the pi bond. Now, you want the discussion of the fall in to make the pi bond? That's the book that's that thick about bonding. And we've never really gone beyond just, okay, let's make a bond. Right? So how many steps did I show here?
2.
2. Which one would you think is rate determining? Yeah, just like SN1, the first one. If we did a reaction coordinate diagram, let's put the alkyl bromide just somewhere here. Of course, this is energy and this is kind of time. I'm not going to do that. Final, I think we could say it's going to be higher or lower than this carbon guy. I think higher. Who said higher? Why higher?
Because that one is sigma bonds,
Two sigma bonds, H and Br, were replaced with what? A weaker pi bond. And if you get out your table and do some calculations, you'll see that this reaction is endothermic. So it's actually sort of up here. Now, where do you want to put the intermediate? What is the intermediate? Carbocation. Where do you want to put that at? It's charged. It's going to be up here. And then when you do this, some type of activation energy leading to that, now you're going to fall downhill. Does it take much energy to fall downhill? No. You just need a little bump, maybe the touch of a feather, and get it to come back down. So this is your rate determining step, your slow step. This is fast. Now which step does the leaving group leave? Rate determining step, just like SN1, SN2. and also E2. All your substitution elimination mechanisms, all four of them, 2 and 2, leaving group leaves in the rate determining step. When we get to organic 2, you'll see leaving group leave in the fast step sometimes, but not here. Okay? Okay. There's an S in an E1. Problem is, this mechanism is not equal. Because that's bad. What's another reason it's not E1?
We have a good nuclear.
A what?
We have a good nuclear bomb. Well, maybe.
It's strong. Strong nucleophile slash base. Everybody agree it's a strong nucleophile slash base? How do we judge strong nucleophiles? Anions or amines. I used to judge strong bases. Anions or amines. It's strong. And if it's strong, what do we say the reaction would be?
E2. Or SN2.
We said E2, but we first said it would be bimolecular, because it could be SN2. If you got a strong base or nucleophile, it's going to be SN2 or E2. That's another reason this is not E1. But I still showed you what E1 could look like. Okay, let's do the correct mechanism. The correct mechanism is going to be called E2. And it's also going to be known as concerted, because everything's going to happen at the same time in your elimination mechanism. Another way to show this is all together now. What if these bond to the H, and at the same time these move in, and these get kicked off? What would all that give? Marco, what would that give? It'd give everything, right? Because right here you're making OH bond, which is in that guy. Right here we're moving electrons in to make pi bond, which is in this guy. And right here we're moving electrons on the bromine to break the carbon-bromine bond and to put an extra long pair on bromine. And it's now minus. All that's concerted. What does concerted mean? Everything happening at the same time. How many intermediates in this mechanism? No intermediates. Did we form a carbocation here? No carbocation. Do you like this mechanism better or worse than the one above? Well, the one above had primary cation, which is bad. Anything bad about this one? Anything you don't like about this one? About this process or mechanism for getting where we need to go? Caleb, anything you don't like about this one? So, over here, why was the first one called E1? Because how many of the substrates are in the rate determining step? Substrates being your thing with the leaving group and the base. How many are involved here? Only the thing with the leaving group. Is the base involved in the ionization? No. E1. How many what is the rate determining step over here?
The only one.
That step right there. The only one. How many of your substrates are involved in that step right there? Both of them. Two of them. So it's called E2. Elimination bimolecular. It's a concerted elimination. A concerted beta elimination. And this is indeed the mechanism for the example reaction. Mainly because you don't form primary carbocations, and so you don't ever do an E1 with a primary halide. Just like you never do an SN1 with a primary halide. Is there another possible way we could have showed this out to get this outcome? Anybody thinking of another way? Another sequence of making bonds, or? There is one other way. Anybody? I'm going to have to redraw this because I don't have to draw down here. What's another way to do this? Well, let me do this. What if I just take the H and leave the electrons behind as a lone pair? That's just an acid-base reaction. Be just removing an H, making a carbanion. And that's going to give your alcohol that we're forming. What if I then move electrons in and kick off the leaving group? That gives everything shown above. Is that mechanism different from the two above? Certainly, because in the two above, we never made a carbanion. Now this, forming the carbanion, would be your rate determining step. And then expelling the leaving group would actually be fast. Because this would be high energy, and when you get to the alkene, you're falling back downhill. So that should be faster. Does everybody agree this is a third mechanism? Okay. Yeah, this is neither E1 or E2. Because we don't make carbanions up there. I'm not going to tell you the name of this one. You're not even going to really see it. Possibly in organic too. Just keep in mind, we're not forming carbanions up there. We're not doing this typical acid base. It either starts with leaving group leaving and making cation, or you do it all together. Also, the leaving group leaves in the rate determining step in both of those mechanisms. Here, the leaving group leaves in the fast step. Okay, you'll never see this again in this course. We'll either be doing E1 or E2. All right, let's look down here at an alternative example. Take this alkyl halide and heat it in T-butanol. It's a neutral alcohol. We can get what looks like an elimination reaction. We can eliminate HBr, so the HBr just kind of comes out, also formed. Now, is this E1 or E2? I hear both. Who said E2? Why E2, Tom?
Because we have a good
All mechanisms we're doing right now require a good leaving group. If you don't have a good leaving group, you ain't going to have. Aaron?
Because you're adding in heat. When you add heat, isn't it supposed to be E2?
I can't hear you.
When you add heat, isn't it supposed to be E2?
No. Why does that make it E2?
Faster?
Heat usually makes things faster. Diels-Alder is going to make it ultimately slower. It's going to make the reaction go the other way. Okay. What type of base do we have here? Weak or strong? Where's the strong base? So how do you judge strong or weak base / nucleophile? Anions or amines? Do you see an anion or amine? No, I don't either. There's no strong anything. There's no strong base. I don't see a strong base. If there's no strong base, we must think it must be weak. T-butanol can be a base, it has a long pair, but it's going to be weak. It's not an anion or an amine. Okay? E2 is bimolecular. E2 requires a strong base or nucleophile. It requires a bully to get up there and be involved in the rate determining step. Ionization to make the carbocation doesn't involve. In fact, all this is the same as SN1, SN2 in determining. SN2 requires a strong nucleophile. E2 requires a strong base. There's no strong base, okay? It's either weak or no base. Okay? Definitely not strong, so it's definitely not E2. We're definitely doing elimination, so it has to be an E1. Now that it's E1, let's do the mechanism. What's the first step? Leaving group leaves. We get carbocation as a rate determining step. What's the next step in the E1?
Beta elimination.
The beta elimination. How do you want to do that? Now, typically, you want to use something to take the H. What something can we use? You can use this. What else do we have here?
BR minus.
I'm going to use the solvent to take it. But we could use Br minus to take it, because if Br minus took it, we would form HBr in the alkene. I'm going to use this because it's there, but it didn't have to be. You could do this without any solvent at all. Let this take the H, move in, and what does all this give? It gives that, well, it doesn't give that directly, no it doesn't. It gives that plus that plus Br minus. This requires more kind of, how do you get this? Here, well, that gives your final product. I mean, that's it. Your final organic product.
Do we also get the cis structure as a minor?
We'll have to talk about that. It'll be fast. Whenever the elimination, removing the H is fast, a strong base is not required. You only need a strong base whenever you're doing it in the rate determining step. Here's a question. In which mechanism, E1 or E2, is the beta hydrogen removed in the rate determining step? Look at your E1 mechanism we did above. Did we remove the beta hydrogen in the rate determining step? No, we did not. All we did in that rate determining step was the bromine leaving. What about the E2? Did we remove the H in the rate determining step? Yes. You better have, because that's the only step we did. All right? If you do it in the rate determining step, you need a strong base. And in fact, if you have a strong base, that's the way it's going to happen. There's a weak base or no base at all. Or we could have had this take the H, and if you had this take the H, we would have formed HBr. Either one you want to do. This reaction could just be heated. You just take this and heat it. It'll probably beta eliminate by an E1. Let's talk about thermodynamics stuff. We've already talked about thermodynamics really when we did this. That's higher energy. Okay? So it's endothermic. Okay? And we explained why over there. So that's your thermodynamics. What about entropy? Is this reaction driven by entropy, yes or no? Brianna? Why? More disorder? Yes. One molecule going to two, because we eliminate something. Yes. More disorder. That's entropy's favorite. Since entropy is favored, will heating make this reaction go? Or is that going to kind of hurt it?
It's gonna help it.
It's going to help it because heat magnifies entropy. And entropy is good. So we're going to magnify the good thing and make it overall better. Okay? If you just take this molecule and heat it up, maybe 200, 300 degrees, you're probably going to do this and start eliminating HBr by ionizing. Okay, different things to consider with this reaction. Regiochemistry is the first. Sort of what Utah alluded to, cis or trans. In the previous reaction, we showed that alkene is trans. Could it have been cis theoretically? Theoretically, yes. One thing we will learn is whenever you do an E1, you always get the most stable alkene. Which one's more stable, do you, Tom? Cis or trans? Trans. The group's opposite, just like in a Newman confirmation. E1 always gets most stable. I'll say it with you. E1 always gets most stable. Okay? Now E2 does not always get most stable. E2, we're going to have to think a little bit more. Let's look at some possible regiochemistry. First off, you got to know when your alkene has possible regioisomers. That is, when your alkene is stereogenic. If we beta eliminate up here, that is, remove the leaving group and a beta hydrogen, and thus put in a pi bond between them where they used to be, we would get that alkene over there. Hopefully you agree. That's a beta elimination reactor, either E1 or E2. Is that alkene stereogenic? No, it is not. There's no such thing as cis or trans for that alkene. So you wouldn't even have to think about it. You would just draw your alkene. Let's look here. What if the chlorine was on the second carbon? And we do a beta elimination. Well, now you got two different things to consider. And so zero. First off, there's beta hydrogens. I'm only going to draw in one. On both sides. So we can eliminate over here and put the double bond in over there, and that would be the same product as that. But we can also theoretically beta eliminate this H and put double bond over here. In this case. Now we got double bonds between the second and third carbon. So now it would be like this. But now this alkene is stereogenic because it can either be E or Z. Now these are stereoisomers, of course. What's the relation between one of these and that one? Those are regioisomers. The double bond's a different region there. Those are regioisomers. So first we have to decide which regioisomer we're going to get. That is, do we want the monosubstituted double bond or the disubstituted? Assuming these two are the same. Then we got to say if we get the disubstituted, is it going to be E or Z? Well, let me ask you this. What if this was done by E1? Which of the three would you get? Let's see, E1 gives most stable. E1 gives most stable. Which one's most stable of the three? Monosubstituted or di? Di. Right? Alkene more substituted? Okay. Of the E or Z, which is more stable? Big groups opposite or on the same side? Yeah. That right there is your E1 product. Now, how would you do this by E1? Do you want to eliminate with a strong base or a weak? Weak. Weak, because strong gives E2.
We just add heat here.
Do what?
We just add heat. It's not bad.
You might could just heat it if it, yeah. Might could just heat it. Or you might could include some silver ion because that helps ionization. We'll talk about that. Something to get it to ionize. Yeah. Okay, that's what we're going to have to do. All right, so the first thing we've already said 2 or 3 times. Okay, the most substituted alkene is the thermodynamic product, meaning it's the most stable product. Most substituted. So those are the most substituted, it's actually stereoisomers. Thermodynamic. I don't think we've seen Zaitsev. Zaitsev is a term used in elimination whenever you get the most substituted alkene. So up here, there's 2 possible Zaitsev products. They're stereoisomers. This is the most substituted, called Zaitsev. Named after some, I think, Russian. And by the way, Zaitsev is spelled like different in every textbook. Some textbooks leave out the Z. Some textbooks actually spell it starting with a Z, like Zaitsev. If you see anything with like Z's and T's and stuff, that's Zaitsev, okay? What is it? Most substitute. Really sort of most stable, but it's... Okay, it's always the major product in E1. Didn't we say that already? E1 gives most stable? E1 gives Zaitsev. We'll do that below. We'll show why E2 gives. E2 gives either. You have to make some decisions. It's not necessarily the most stable in E2, which can often give the less substituted. By the way, the less substituted is called what product? Hoffman. So this guy over here is the Hoffman product for the above reaction. Hoffman is just a name for the less substituted alkene. So let's do it. This is an E1 example, okay? If you just take this and heat it in water, you can beta eliminate. Since it's E1, do we expect the double bond to be put on this side or down?
Middle.
In the middle. So we're going to lose that H. Put the double bond in the middle. Because that would be the more substituted. So this is what? Zaitsev? Hold on, something wrong here because
How'd that look like?
there's no isomers here. Are we missing carbon? 3, 4, 5. 3, 4, 5. Must have fell asleep. There's no E or Z there, right? That alkene's not stereogenic. Y'all want to make it stereogenic? Let's make this ethyl up here. If that's ethyl, is the ethyl group going to be cis or trans to the methyl? Trans would be better. Put it right there. Now that applies. Maybe you've already marked it down. It'll be E, opposite. As drawn, there was no E or Z. Everybody see that? Because we know E1 gives the most stable. E1, most stable would be Zaitsev, but also E. Big group's opposite. Okay, in summary, we've already said it. What about E2? Let's do an E2 down here. Now for E2, we need a strong base. So I'm going to include a strong base, like hydroxide. And in E2, it's all concerted. The base takes the H. Electrons move in, kick off leaving group. And what does all this give? Right here, we're forming water. Right here, the leaving group is leaving, Br minus. But right here, what are we doing? Moving electrons in to make pi bond. We get our alkene. And this is the State-Step product. More substitute. Thermodynamic product. Let's talk about it a little bit. It's most easily formed, or it's easily formed with an unhindered strong base. Which has no problem extracting the more hindered beta hydrogen. Ah, what do we mean? Realize this. To put the double bond here, the more substituted double bond, to make the State-Step product, we have to eliminate HA. Here you eliminate HB, and that would give the Hoffman product. Which H is more accessible to the base, A or B? B is more accessible. A has these other groups around it. Okay? I don't know how to spell accessible. That's the less accessible H. A small base doesn't have any problem taking the least accessible hydrogen to make the State-Step product. Let's look at the difference below. Below, our base is now more sterically hindered. Now our base has these groups on it that add like wings. And now as they want to approach the H, the wings kind of get in the way. Okay? So now we have a sterically hindered base. It's more bulky. It's going to have more difficulty getting to that H. The more bulky your base, the more prone it is to take the more hindered hydrogen. But if you take that H, which product do you make? You make the Hoffman. The more sterically hindered your base, the more likely you are to get Hoffman. Which is actually the least stable. That's one reason the Hoffman may be more favored. Because remember, the base taking the H is involved in the rate determining step of an E2. But that's not the main reason you may get Hoffman. The main reason you may get Hoffman is number 2. And each elimination has a stereochemical requirement. And in D2, the leaving group and the beta hydrogen that's being extracted must be coplanar. Okay? E2. E1, none of this matters, and in E1 you always get most stable. Remember? E1 gives most stable. How about E2? E2, the leaving group of beta hydrogen must be coplanar. With anticoplanar preferred, highly preferred, anticoplanar is sometimes called antiperiplanar. Syn coplanar also works, because it is coplanar, but it's not preferred. What do we mean by coplanar? Well, if we're going to beta eliminate here and here and put the double bond in here, and if the bromine is drawn up on the board like this, that means the board is plane. Pretend it's drawn here, okay? I'm just going to step out. Now, if the bromine is drawn there, if the H is coming towards you, are they coplanar? No, they're not. How does the H have to be if the bromine is like this? It has to be in the same plane. Now I'm in the plane as a board, flat like the board. HBr. Now is this, if this is the central line, is this anti or syn coplanar? anti, they're opposite. Okay? Now what if this is the central line and they're both like this? That'd be sin. But see, in both cases, they're all in the plane of the board, either both this way, both this way, the plane being right through here. If they're like that, you can't eliminate them. They're not coplanar. Now, that's anticoplanar with the plane being here and it's on the board. If we remember our Newman, if we look down the bond, that's anticoplanar. BR straight up, look down the bond, the H is in the back. See, here the plane is like right through this rail here. Both of these are on the plane. So they're coplanar. If one was like that, they're not coplanar. Now, are these anti or sin coplanar? If we were doing Newman, that would be sin. Now, if I rotate the H down, it's still the plane of this rail, but now it's anti. And that's preferred. That's how I've got it drawn here. BR in the front, the H is in the back, straight down. See, the plane is like right through this. That's sin coplanar, sort of analogous to this. And if we made this sin, it'd actually be eclipsed. Now rings. Let's look at the rings, and then we'll take a short break, and you can sort of look down below while we're taking a short break. And rings, cyclohexane, these are anticoplanar. You can actually look at this. And one thing about the cyclohexane, for the H and the leaving group to be coplanar, the leaving group has to be axial. You have an axial. Let's pretend like this is a leaving group. Let's make it axial, so I'm going to do a ring flip. Let's put it down, it's a little bent. And that's kind of perfect right there. Okay. If I agree leaving group is axial, straight down. Look at the hydrogen next door. First of all, there's two different carbons to choose from. Either one's the same here. On that carbon, there's two H's. Which hydrogen is coplanar with the leaving group? This one? Yes, that one. Not that one. Where's the plane? Plane is right through there. I'm going to show this side of the plane. See right through there? The BR is straight down. The H is straight up in the plane. Is the H and the BR sin or anti? Anti. Okay, straight up in the back, straight down the front. Okay. Bromine is straight down, axial. The H that gets eliminated is straight up and also axial. How about the other H on that carbon? Is it in the same plane as the bromine? No. If the plane is this way, that other H is sort of coming like that a little bit. See, it's going like that? It's not coplanar. Only that one. You see how that hydrogen is not in this plane right here? You see how it's like this? Only that one is. And if you did an E2 here, that's the H that would be removed. Let's do a ring flip. Do a ring flip. First off, what position is the bromine now? Axial or equatorial? Should be equatorial because we need a ring flip. Okay. Now it's equatorial. And by the way, is this the preferred or not preferred conformation? Now we're in the preferred conformation. Okay. There's the bromine. Equatorial. I'm just going to hold it like this though. Let's look at the neighboring hydrogen over there. Is there an H? I'll show this side first. Is there an H that's in the same plane? Here's an H. Is that in this plane? No, it's coming this way. There's an H going in the same plane as the bond going down, but that's not an H. What is that? It's a bond to another carbon. So there's no H that's coplanar. What about on the other carbon? It's going to be the same thing as I just showed you over here. The other carbon, is there an H planar to the bromine? No. Here's a plane. One H is going that way, there's a bond going straight down, which is in the plane, but the bond going straight down is not a bond to H, it's a bond to carbon. Okay, when the bromine is in the equatorial position, there's no H that's coplanar. Leading group must be axial to be coplanar to a beta hydrogen. Show you the same thing here. This H is coplanar, straight up, straight down. That H is not. So if this beta eliminates, that's the H that will be removed. And note that the elimination takes place from the bad conformation. That bromine would rather be equatorial. But if it's equatorial, it can't eliminate. So it actually eliminates from the bad conformation. Okay, let's take a 3-minute break or so, and then we'll do some of the problems below. Working in the stereochemistry outcomes.
I was gonna do that later on after lab. I got pretty good at the front, the top front end, so I did a test of like 100 and only missed 15. So, back on.
Okay, guys. Let's look at the first one here. I see a carbon with a leaving group over here. Yeah? Tetrahedral carbon with a leaving group, so we can do substitution or elimination. We now know 4 mechanisms: SN1, SN2, E1, E2. Is the first which of the 4 is the first reaction?
E2.
I hear an E2. Anybody else? Why not E1?
We have strong nuclear carbon.
We have a strong base, hydroxide. Hydroxide's strong. If it's strong, it's going to be bimolecular. So it's either SN2 or E2. Why not SN2?
It's tertiary.
Those are leaving groups on tertiary carbon. You don't do SN2 on tertiary carbon. This is all set up to do E2. But you have to evaluate the reaction. Make choices. Okay, now that it's E2, do you have potential for Regio isomers in the outcome? That is, do you have potential for Hoffman and Zaitsev? Why not, Zach?
Because the H's that the beta H's that you would remove aren't anti-coplanar.
Let's not do that yet. That's going to be stereochemistry. Just double bonds. Where are we going to put the double bond in? Basically, when you ask this question, you're looking for how many types of beta hydrogens. I see a beta hydrogen here. Everybody agree that's a beta hydrogen? The carbon that the bromine is on is alpha. It's a beta hydrogen. And so if we eliminated it here, we'd be putting a double bond in here. That would be one regio. That'd be one region for the double bond. Could we put the double bond in somewhere else?
Could you take off the H from the methyl group?
Sure. There's 3 of them there. That's the alpha carbon. That could be beta. And so you can eliminate A or B, put the double bond in there. Very often you guys don't consider carbon-carbon here because it's bolded, you're like, you can't do anything there. No, you can't. Basically, how many beta carbons is here? 1, 2, there's a beta carbon. Is there an H there? See, you're not going to put a double bond down there because that carbon can't make 5 bonds. There's no H to eliminate. Are we going to eliminate A or B? First off, names. If we eliminated A and put the double bond in there, how many substituents? Would that be Hoffman or Zaitsev? Or B? Somebody tell me which is. If I put a double bond in there, how many substituents would it have? 2. These 2. If I put a double bond in there, how many substituents would it have?
4.
Actually 4. Boom, 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 without the bromine. So what do you want to call this product? Zaitsev. And this product would be Hoffman. I'm pretty sure Hoffman is 1 F and 2 N's. Is that what it was spelled on the previous? Okay. So which is more stable, Zaitsev or Hoffman? Zaitsev. Zaitsev is more stable. Of course, this Zaitsev would have stereochemistry. Because the 4 groups could be E or Z. Everybody agree we're doing E2? Which product are we going to get, Zaitsev or Hoffman? The answer is it depends. E2 depends. If we were doing E1, the answer would be Zaitsev. We're not doing E1.
Could we say the major product here?
We're looking for major. Everything I'm asking you, what's major?
Would
Okay.
it be Zaitsev?
Do what?
Wouldn't it be Zaitsev because it's not bulky?
Good. You've addressed something else. Is the base bulky or not? Hydroxide is not bulky. It doesn't have like substituents for that. So should hydroxide have any, well, you always want to make the most stable if possible. Possible we want to make this 8-7. Does hydroxide have much problem taking that HA, which is more hindered, by the way? It's just more deeper between the alkyls and everything. It shouldn't have as much problem. So we're using a good base if you want the 8-7. But what was the other requirement for 8-7? Or for any E2? We just ended with it. Yeah. Okay. Now, I'm not going to tell you everything. I'll tell you, but we'll have to further address it as we go along. You are going to get SATSF here. Okay? Because the base is able to eliminate, you get SATSF. So here's a question. Draw the SATSF product. Draw the SATSF product of this reaction. So I'm putting double bond between there and there. That has an ethyl and a methyl, and this has a methyl and a what? And a terbutyl. Did anybody get anything else for the SATSF?
The cis formation.
What?
The Z formation.
This is E, and this is Z. They're both SATSF. Which one's going to form?
The Z, because they're
Which one's going to form?
syncopate.
Andrew? Which one going to form? YE. Painted? Which makes it the most stable? I agree, E is the most stable. But does E2 always get the most stable? What type of requirement must we meet? The beta hydrogen in the leaving group must be what? Anticoplanar. Andrew, are you sure that the H in the leaving group can be anticoplanar when we're looking to form E? Because if it can't be, then we can't make E. How are we going to determine if the H and the B are? Here we go. Let's see. Here's the molecule. The bromine is green, and it's back. T-butyl, there we go. The T-butyl, instead of having other carbons, just the red is the T-butyl. Okay. Up here, methyl's forward, bromine back, bromine green. And here we've got this other carbon. The ethyl is forward. And then that can swing any way it wants. Straight down is the methyl. What's going back on that carbon? Hydrogen. That little guy's the H. And actually, that little guy is the guy we're going to eliminate, right? Okay. Well, right there, the H and the B are coplanar. You see the plane right through there? But are they syn or anti? Are these syn or anti? Those are syn. There's the bond. Okay. Is syn preferred or is anti preferred? Antique. So this needs to actually rotate like that. Now the H and the bromine are anticoplanar. And now the reaction takes place. What's the mechanism? Base takes H, electrons move in, leaving group all at the same time. And when all that happens at the same time, the groups are fixed. And now the double bond ends up in the plane. And on this side is the ethyl and the T-butyl. The alpha and the T-butyl are on the same side. So which do we get? Here's the plane. We actually get zinc. Which is not the most stable. Right? Not the most stable, is it? Okay. Easy most stable. We have to meet the stereochemical requirement. Now you might say, well, why didn't it eliminate syncoplanar? Syncoplanar would give heat. Anticoplanar is highly preferred. You always do anti unless you can't do anti. Would you like to draw this on the board instead of just doing it with a model? Or you just want to always do it with models? You want to also see it on the board? Okay. Do it on the board. We need to be able to draw this on the board in a certain, so it doesn't get all cumbersome. How are we going to do that? Newman. Marvelous idea. Let's try Newman. Newman's a lot easier to see this. That's why Newman created the Newman projector. Let's draw this in a Newman. Let's put the bromine in the front. Let's draw it a Newman like this. I'm looking through there. And so this is going to be carbon 1 and 2. One's in the front, two's in the back. Circle, circle, dot, dot. Carbon 1, what's coming, if I look through there, what's coming straight down on carbon 1? T-butyl. What's coming towards you on, which is my left on carbon 1? Methyl. As I'm looking through there, what's going to the hull, and that's on my right? Bromine. Now let's look on the back carbon. Past 1. On 2, I see something going straight down. What is it? Oh, these are actually eclipsed. Straight down. So I'm going to draw it just a little bit to the side there. It's eclipsed. Since it's on the back, it's coming out from here. Back carbon, something coming towards you. Ethyl. So it's on my left. Ethyl is on the left. It's also eclipsed. And then on the back, on carbon 2 is something going to the hull. That's that H we're eliminating. Actually, as drawn, the H and the Br are planar. Remember when I first showed it to you? They were. But these are not anticoplanar. These are what? Syncoplanar. And they're also eclipsed. That's not a great confirmation. What do we need to do? We need to rotate. And this is exactly what I did. I was showing it to you. What did I do? Didn't I rotate it? Well, let's rotate it on the board. I'm going to rotate the front carbon. Where do we want the bromine to be? We want it right here. So I'm going to rotate this here. I'll make that a little shorter. We just rotated the front. The back still has H. Methyl. I should have rotated the back. It doesn't matter. The front is, the back here is. Oh, I switched these. Yeah. Ethyl's on the back, so methyl. And then here it looks like the methyl's on the back. Now we're going to rotate and make the bromine over here. And when the bromine comes here, where does the methyl go? Actually, it's all going to go kind of, we're doing a 180-degree turn to the front carbon. The T-butyl goes straight up. Now look at this. Now your plane is right through here. And the H and the Br are sitting on that plane, but now they're what? Anticoplanar. So then we eliminated. We actually put the double bond in between the two carbons, but at this point you're done, because at this point you have two sides. And then whatever you see here, you're going to get there. But what do we see? The T-butyl and the ethyl are on the same side of the plane. When it eliminates T-butyl and ethyl, here's your plane here. That's what you get. Because it's all governed based on the requirement of the H and the Br being highly preferred to be anticoplanar. So that thing rotates and then it puts in the double bond. So we didn't get the most stable. How would you, if you wanted to make this product, how would you make this product? What type of mechanism would you need to do? Not E2, but E1 would have given that product, because that. And if you want E1, what type of conditions do you use? Do you use hydroxide? You need something weak. Usually just like solvent. Okay? Do the second one. What's going to be the major problem? Let me give you sort of a little hint. Hint to remember. Unless you're dealing with rings, this is a non-ring or acyclic. Cyclic, acyclic. We can put the double bond in over there or here. Over there would be Hoffman, over here would be Zaitsev. Over here, to make the Zaitsev, we got to remove this H. But the only time you have to worry about what we just did, anticoplanar, is when you only have one H that you're over there. Okay? Only one H. If there are two H's, you don't have to do this. If there are two H's, you're going to get the most stable stereoisomer. You only have to do this when there's one. For example, here, if you're going to make this double bond, there's only one H over here, you got to make sure you do this. Over here, there's two. It does not matter. Why does it not matter? Because you can rotate both and make them both in the right position. And since you can do both, something else has to decide your outcome. What decides the outcome? The stability of the products. So if you eliminate over here, you would just draw everything trans, because that's going to be the better conformation. Okay, is this going to give, there's some questions here. Is this going to give Zaitsev or Hoffman?
Hoffman.
Why Hoffman?
Sterically.
Yeah, that base is very sterically hindered. Let's get rid of that guy. It's got these huge wings on it that keep it from getting into tight spaces. And that H there is a little more buried. Hindered base. Now we have to clarify this. Makes Hoffman more favored than if using sodium hydroxide. Here's the problem, guys. A sterically hindered base doesn't automatically make Hoffman the favorite product. It just makes it more likely to be a favorite product. And here's the problem. Some textbooks will show you, okay, sterically hindered base is going to be Hoffman. Other textbooks won't. They'll just say it's more likely to be Hoffman, but it still gives Zaitsev. So what are you supposed to know? Well, here's how I usually will handle this. I will maybe show you both reactions and say, if you wanted Hoffman, which base would you use? KOH, sodium hydroxide, or sodium O with all the wings on it? If you wanted Hoffman, which base would you use? One with the wings. Now that may not be the major product, but you're going to get more of it than if you use sodium hydroxide. Or I may ask you this. I may show you the reaction and say, okay, show the Zaitsev product. So I'll give you some information. So let me do this. Why don't you do this? For the sake of the reaction, show both the Zaitsev product and the Hoffman. Label them. And if they have stereoisomers, show which is the major stereoisomer. That should be, you should be able to do. Show major stereoisomer for each. The Hoffman should be the easiest because with Hoffman you don't have any stereochemistry really to consider issues. Okay, we need to move on. I need to actually ask you to do that overnight. Okay? We'll look at it tomorrow. Let's do one with a ring. TEA is triethylamine. That's your base here. Is it strong or weak? It's strong. Now, it's not as strong as the sodium hydroxide, but it's still considered strong. Okay? THF is just a solid. Triethylamine is a sterically hindered strong base because it's got these wings on it. Triethylamine is commonly used for E2 because it's a sterically hindered strong base. Now we haven't talked about substitution yet compared to this. All your eliminations compete with substitutions. For example, you could just substitute this off and have the amine attack here and kick it off. We have the nitrogen body there. But the sterics keep that from happening, and because for this acting as a base, it's not quite as important. So because it's sterically hindered, your SN2 is not great. Now, it's here. We can either put double bond in there by removing one of those H's, or we can put double bond in here by removing that H. Let's label these as A, B, and C. Those are actually the same right now. Which H do we have to remove to make the Zaitsev product? C. Put the double bond here with the ethyl substituent. Okay? Now, the question becomes, can we remove that H? What's the requirement? The leaving group in the H must be what? Anticoplanar. Is the I and the H anticoplanar? Well, anti is synonymous with trans. Are they trans? No. I'm sorry, let's put in, this is chiral, so one of these is forward, and one of these is back. Let's draw this in a chair conformation. Let's put the iodine right here. To eliminate, does the iodine need to be axial or equatorial? Axial. Now that's there. Let's put the ethyl here. Is the ethyl axial or equatorial? Well, the ethyl is trans. So what is trans here? Axial. These are trans. And so the H here is what? And that is H what? C. HC. Is that H and this H anticoplanar? No. Showed it on the printout, showed it on the model. That's straight up. This would have to be either straight up or straight down. Is it straight up or straight down? No. The ethyl is anticoplanar. See? Basically, the fact they're cis tells you you're going to get this problem. These cannot be eliminated. You cannot get the same set product. Let's look at these two H's. There's a down bond and there's an equatorial bond. Now they're both H's. Which one of those is A? Well, A is cis to the iodine. Which one's cis to the iodine? A. That makes this B. These are trans. Of those two H's, which one is anticoplanar? The iodine is straight up. Which one is straight up or straight down? That one right there. That's the one, that's the only one of the three that can get eliminated by E2. This reaction only has one product. That one up there, you can show both and say which is major, which is minor. This only has one, and the one product is this. Double bond's going to be here. Which H will be remaining if I label them? HA will be remaining because HB gets eliminated. And down here is what? Still the ethyl, and we didn't do anything, it's still there.
So if HB somehow is not available, would you say then there's no reaction?
Good. If this was like a methyl there, it would not eliminate. Your ring flip, still nothing is coplanar. I was thinking, could something be syn-coplanar? Syn-coplanar can work. No. To be coplanar, the leaving group has to be axial. And there it is. These are your two coplanar bonds. That one's taken by another group. If that was a methyl or something else, yeah, it wouldn't eliminate. In the end, it's easier in the ring though because you can't rotate. Anticoplanar is the same as transcoplanar. They have to be trans, and in a ring you can see that. You see how B and that are trans? But there also can be coplanar, as shown here. Here's where you see the transcoplanar. But they have to be trans. So you can. Okay, that right there helps you to answer questions such as below. Which reaction would be faster? The one thing we have to keep in mind here is that if you're asked to draw the best comparator of this compound, would this be the best comparator? Iodine and ethyl both axial? Is that the best conformer? No, best place for those groups is what? Equatorial. When we talk about faster, what's really getting at is how often does this exist in the right conformation? Is the other conformer just as bad and so it's kind of back and forth between them both? Or is the other conformer really good and so it's over here? Basically this, if your equilibrium is like that, and this over here being better, it's not going to eliminate fast. But if your equilibrium is like this, and it's always in this conformation, it's going to eliminate faster. That's what the bottom gets to. It's kind of getting to. So think about that. There's many more in the workbook, and there's probably more in this handout. Let's move on to some miscellaneous things. Please be doing some of those problems overnight. We'll look at them tomorrow. Let's summarize. E1, weak base or no base at all. What product do you get with E1? E1 gives HF. E1 gives most stable HF. So if this HF has possibilities, it's going to be E, trans. What does E2 give? It depends. HF is preferred. If you can, in that last reaction of green, did we get HF? No, we got Hoffman there because we could not do HF. E2, you have a stereochemical requirement you have to meet. If it's not cyclic, you can usually rotate it and get it, but once you rotate it, then that defines your stereochemical outcome and you may get Z instead of E. Okay? And there's other miscellaneous things that will come up from working your questions. Hopefully you'll have questions tomorrow. Okay, miscellaneous things. When either substitution or elimination is possible. Now we're going back to say, okay, could it substitute, could it eliminate? We're considering everything here. First off, heat favors elimination. We've already said that earlier today. Heat favors elimination. For example, you could also get a substitution product there. What's the substitution? What would be the substitution product? E2. What if you were asked to show a substitution product? First off, it would be SN1 or 2.
1.
SN1, because we've got the big nucleophile. What would the SN1 product look like? Well, we're making cation. Let me see if I can get to it. We're making cation.
Rearrange.
Water could add here, but it probably rearrange, wouldn't it? So you're saying that that's a better cation? Yeah. And if you can rearrange, always do that. Water adds to it, and so we get something that looks like this. But then like Br minus takes the H, and you end up with like that. See, this is your SN1 product. Is that?
Why'd you put E2 under that?
I'm not sure. That's E1. Thank you. They can both potentially occur. But if you heat this, especially heat it higher than, gets higher and higher, as you heat, which starts to become favorable.
E1.
Elimination, because when you eliminate, you're going from one molecule to two. When you do substitution, you're not going from one molecule to two. You react that with water, you get this plus what? That with water is two molecules. You're going from 2 to 2. There's no entropy there. Your heating is going to favor your entropy process. Well, I see I already had this SN1 down here. Why didn't somebody tell me? All that was right there. SN1 product. All right. Remember that, but we mentioned that several times, right? Another thing. The better your nucleophile, the more the substitution is favored. A good nucleophile will favor substitution, while a poor nucleophile will typically get elimination. For example, if you react this with HBr, and by the way, I did show rearrange. Here I got a different, okay. HBr, I'm showing that. So that's SN1.
So with a poor nucleophile, usually just favor E1. Or can you have E2?
Poor nucleophile, E1. Br minus is a good nucleophile, especially compared to this one. What's this nucleophile? Which is a better nucleophile, Br or F minus? Yeah, because it lets this lone pair get out there, okay?
Why wouldn't that be SN2, the HB?
Keep going, ask me, why do you ask that? I think I know, tell me, why are you asking that? Oh, I thought it was, thank you. Okay, what made you ask that?
Because IBR was a stronger.
Okay, it's an anion, right? Good. According to our definition, anions. The thing is, Br minus is sort of an exception to that. Your halides, while there are anions, they're not great nucleophiles because Br minus likes being Br minus. It's pretty stable. So you're right to ask that. Another thing, if you're under acidic conditions, you really can't have a strong base / nucleophile. So it is an anion, but it's not. It's better to do, the example is better to compare. Which is stronger, Br or F? Which is stronger? Nucleophile, not base. Yeah, and because of that, it typically prefers substitution. Okay? The worse your nucleophile gets, the more prone you get to elimination. There's a question over here. So there's a difference. And here we go. That's what we just say here. Now down here, what are we doing down here? Obviously the oxygen's leaving. How do you make oxygen a better leaving group? Protonate it. Can you protonate it? Yeah, we have a strong acid. I'm showing an elimination product. Is this E1 or E2? What does E2 require? Strong base, right? Can you have a strong base in sulfuric acid? No, you're in a strong acidic condition. There's no strong base here. This is E1. What is the conjugate base here? HSO4 minus. It's a terrible base / nucleophile. Never use it for anything. There's no nucleophile here to do a substitution. Since it's E1, what do we do mechanistically from there? Carbocation form. We could rearrange, but either way, you don't have to. You can get the same product here. Let me do it without rearrangement. There's an H here. How do you go from here to there without rearranging? Something needs to take the H. Okay? But here's a fast step. You can use this, or you can use water, because that's an aqueous acid. Either one, put the electrons in, and you get your final. If you use sulfuric acid, you'll reform H2SO4. If you use water, you'll make H3O+. But that's what sulfuric acid is, it's H3O+, right? But removing the H here is the fast step. Easy. Any lousy base can do that. What this illustrates is it's very common to dehydrate an alcohol by an E1 mechanism. That's what we did here. We dehydrated it because if you forget that, that gives this plus what? Water. So we removed water. We dehydrated by an E1. That's a common reaction of alcohols. Actually, at the beginning of organic 2, I covered that reaction. On the other hand, if you treat it with HI, you'll get the substitution product. Why? Because iodine's a good nucleophile. And the better your nucleophile, the more favored substitution. Okay, there's a few more miscellaneous things that we'll cover, including using a polar solvent, like was mentioned very earlier today. Finish this up. I still think we need to go back to the Diels-Alder and do some, the ones that were in the handout. What else we need to do tomorrow in preparation for Wednesday? This is the last handout. We end with eliminations.
Oh, I would, or, when you do realize it's substitution, I don't know if it's like this division between S1 and E1.
That's a good question. SN1 and E1 often compete, but the better your nucleophile, the more prone you are to get SN1. I minus is a great nucleophile.
But wouldn't that be SN2?
It's not that good. See, there's a conflict. What if your big group is on a tertiary carbon? There you go, so you can't do SN2. Okay? So often you have competing thoughts with something maybe decides it for you. I have a big flow chart that tells